Hello, and welcome to the AIA DC webinar on as-builts. Today we'll be covering the best practices for surveying, drafting, and modeling as-built plans. I'm Justin Yoder, and I will be your sole presenter today. I'm the Regional Director of the Mid-Atlantic Office for Precision Property Measurements. For over 21 years, PPM has been delivering as-built surveys to architects like you across the country. Given my tenure in the industry, I've been fortunate to observe the production methods change over time. So during this presentation, I'll impart not only some of the best practices for as-built production, but some of its history and evolution as well. This course will demonstrate the best practices for creating as-built plans and drawings to be used as the foundation for architecture projects or urban design and planning. Some of the learning objectives will be learning to begin a project by determining if as-builts are needed. 2, understand the scope of work from an as-built only perspective to get a head start on creating design elements, construction documents, and obtaining permits. 3, obtain as-built plans for all levels of scope through new and effective methods such as LiDAR scanning and 3D photogrammetry. 4, put down collective data in both AutoCAD 2D format and Revit 3D format. First, what are as-built plans? We'll talk about common definitions, when as-builts are needed, gathering various degrees of information, and the details of the scope that may be needed. Then we'll cover gathering on-site information. We'll discuss briefly some traditional methods to get measurements, and then jump right into terrestrial scanners versus mobile, point clouds, and using point clouds. And then last but not least, creating an as-built set. We'll finally discuss using the point clouds created by the scanners to create a set of as-built plans. I also want to point out that throughout the presentation, we're going to have a series of polls in which I'll ask you all multiple choice questions. And at the end, we can open it up for questions if you have any for me. So what are as-built plans? Let's go through some common definitions first. When looking into the actual definition of as-built plans, what one will mostly find is a definition that concerns as-built plans being created after or during new construction or after or during a renovation. As-built drawings are prepared by the contractor. They use red ink to show on-site changes to the original construction documents and are more like interpolations done for construction purposes. Therefore, the changes that the contractor makes onto the original design are called as-built drawings. Contractor-developed as-builts should not be confused with record drawings, created, of course, by the architect or engineer. Record or archive drawings often include the information gathered on as-builts and are the final set of formally developed prints fully signed and stamped by the project engineer or architect. This definition reads, prepared by the architect, reflect on-site changes the contractor noted in the as-built drawings, and often compiled as a set of on-site changes made for the owner per the owner-architect contract. This set is not always mandatory and created, but in general, some formal architectural services create these as one of the last tasks of a building project. And of course, everyone here takes the time to do this on every project, right? All right, first poll, just type your answer by the choice in the chat. How many times has a contractor you've worked with actually created as-builts for you as described? A, never. B, sometimes, or C, always. Again, go ahead and just put your answer in the chat if you wouldn't mind. It'd be nice to get a little bit of a understanding from all of you. See a lot of B's, so we have some work to do, a couple of A's. Thank you, Amanda. Few A's. All right, great. So for those of you that have A's, it'd be nice to know maybe later, you know, how you're getting your as-builts. For those of you that have B's, and sometimes, again, it'd be nice to be able to. Hopefully, this presentation will help you get a little bit more information. Actually, the A's were never. All right. Well, we'll move on. Hopefully this presentation will help better understand what should be provided and what we provide with ours. So again, what is an as-built plan? Let's just keep it simple. I think we can all agree in the architecture and construction industry, as-built refers to a drawing that shows the existing dimensions and conditions of a building, space, or area. Before we get any further though, I just want to say that throughout the presentation, we'll be discussing producing as-built plans in their final format as either a 3D Revit model or 2D CAD files. Both are softwares created by Autodesk, and as you likely all know, there are many, many other drafting and modeling softwares out there. So even though I mention Autodesk software specifically today, it's likely you can apply any points I make about 2D drafting software to all others on the market, as well as other 3D modeling softwares. Pretty much whenever we're working with an existing building, we're going to need as-built before starting design. If the owner or client happens to already have as-built drawings, then we may just need to enter them in CAD or reformat them if they are already in CAD, and confirm the drawings are up to date. If errors or inconsistencies are found, then at some point you may decide that a fresh set is needed. So when aren't as-builts needed? It is rare that clients already have current as-builts of their existing building that are accurate, but it does happen. So in that case, of course, you would not need more before starting your project. There are also simple cosmetic projects that do not require having accurate as-built plans. And of course, if a building is being built from scratch, then all you'll need are the construction documents. So when is the best time to obtain as-built plans? In most cases, obtaining as-built files is one of the very first steps in the renovation process, if not the first step. Getting ahead of this step allows an architect to focus on their design, plan creation, and submittal to the building department, all of which are considerably more time-consuming than the first step. There are also cases where you'll be working with the historic review. They will require as-builts be created. Most engineers will want a fresh set of accurate as-builts before they begin a seismic retrofit project. And if you are working on a teardown project, some building departments will require you to submit as-builts of the structures being demolished. So what are some other contributing factors? As-built, as mentioned on the previous slide, different municipalities work differently and have different requirements. If they require as-builts for any reason, the type or the scope needed may vary from city to city. If you plan to preserve or improve upon detailed architectural elements such as ornamentation, you'll need to consider that documentation and where it fits in your timeline. Overall, the size and the scope of your project will determine when as-builts are needed. And as we'll discuss in the next section, to what degree the detail and scope of the as-builts are required. So you've discovered you'll need as-builts. How far or in how much detail do you need your information to go? Above are a few examples of plan types and when they're needed in your as-built plans set. You might need floor plans most of the time, almost always. Exterior elevations when the work impacts the exterior of the building. Sections when you're working with height constraints or vertical relationships between spaces. And reflected ceiling plans when modifying existing lighting or working with unique ceilings. It is ultimately up to you as the architect to decide what the scope should be for your as-built plan set, or consult with your engineer as well on what is needed. Before we get into specifics regarding plan types, let's go over some of the ways to gather on-site information, starting with a very simple, quick method and then ending with some full-blown as-built plans. One way to obtain the answers you need on-site before a renovation is by simply taking photos. This can assist in the design process and answer questions you might have before proceeding. Sometimes a simple, quick single line or even a bubble diagram is all you need to achieve your goal. This can be achieved quite quickly on site and does not need to be to scale. Sketching can be very helpful in supporting your design. In the case of interior elevations or perspectives, this can also be done roughly and may not require measurement. And if drawings need to be to scale, such as when they'll be used to create new construction documents, then you'll need to go to a higher level of accuracy and measure the existing conditions. How you get these measurements can vary quite a bit, as you'll see throughout this presentation. Most remodel projects will require a more detailed scope for as-builts. This will give you a head start in the creation of your design, submittal, and construction documents. And so to sum up the first portion of this presentation, as-built plans, simply defined, is a set of plans of any structure as it exists at that moment. They're most often used for a renovation of some type. Getting as-built drawings in the format in which you work is important, such as a particular software. And last, the scope of the as-built plans and the detail of each scope item will vary with the needs of your project. All right, so moving on to gathering on-site measurements. This presentation will mostly be about scanning to obtain your measurements, but I wanted to touch on a method that is still near and dear to my heart of getting your measurements, which is what is now known as the old school way. This is where you take the measurement you need, write it down, and then bring it back to your office, or you take the measurement you need and then walk over to your laptop and enter it right into CAD or Revit, right there on location. You can use a tape measure to measure lengths, obviously, of anything. And for heights, you can measure all the risers and the stairs, drop it down a balcony, run it up a wall, etc. A laser distance meter, or disto, can perform trigonometric functions instantly and get you lengths and heights in all sorts of ways. Some come equipped with a camera feature as well, which really helps with long shots. The first two of these tools you might already be using to measure for your plans, but the third is used exclusively to gather height information. That is the zip level. This is an excellent tool invented, distributed, and repaired, if needed, by a company out of San Diego. I'm not aware of any other version of this tool, but it uses displacement to read heights anywhere within a 50-foot radius. These are great tools, and if you use them well, you should be able to create excellent as-built plans with them. There's a part of me that still misses getting my plans done this way, but the industry has moved on and there are better tools out there, which we'll be discussing soon. But first, another poll. Again, enter your answer in the chat. How comfortable are you with sketching and measuring as-builts? A, very uncomfortable. It makes me sweat just to think about it. B, I've done it, but I don't like it. C, I am comfortable doing this. And D, I always sketch and measure my as-builts. I love it. So far, a decent amount of comfortable and always doing it yourself. A couple of Bs. So hopefully, for those of you that are comfortable doing it or always sketch, hopefully this will open up some opportunities for using some new technology that we'll be talking about next. Thank you for all of your answers. When we do the Q&A, I'll have one question for all of you as well, in addition to these polls, and I'll be curious to know your answer to that as well. The change to a completely new technology and ditching some, if not all, of the traditional methods isn't easy in any industry. And as I admitted, and I was admittedly skeptical myself at first, but using LiDAR does allow for fast data acquisition. It's more accurate than any measurements that can be taken by hand, and thus reduces the odds of human error dramatically in the field. It's technology that can be purchased, rented, or contracted. It's a thorough solution, allows surveyors to gather more data than needed to complete most projects, and provides a digital twin to pull additional data down the line if the project ever needs to be revisited or additions need to be made to the scope of work. Here are some examples of each type. There's terrestrial or standing scanners, or mobile or walking scanners. LiDAR is a method for measuring distances by illuminating an object with a laser and measuring that laser beam's reflection with a sensor. LiDAR stands for light detection and reading. Each one of these illuminations can be considered a measurement. Each single measurement is then logged, and throughout the course of the scan, millions of measurements are taken in all directions. Either way you choose to go, you'll be using LiDAR to create a point cloud. So let's talk for just a minute about terrestrial scanners. And here are a couple that our team uses and are familiar with. First, the Faro Focus. Overall, you'll find that terrestrial scanners like this one will give you a much cleaner and a much denser point cloud than a mobile scanner will. The problem is that they're terrestrial, meaning they need to be mounted and stationary while scanning. This limits your ability to maneuver and get in tight spaces, and it can take some time to set up and break down on site. And here is the Leica RTC 360. Even though this needs to be set up on a tripod, like the Faro, the individual scan times for the RTC 360 are relatively short compared to other terrestrial scanners, making it the fastest terrestrial option out there. The iPad app also helps make sure you can check your point clouds before leaving the job site. The RTC 360 is extremely precise, but some terrestrial scanners offer even higher levels of precision in the resulting point clouds. In the next slide, we'll see a short video of a scan taken with this scanner. While our other scanners can be moved while they are operating, the RTC 360 needs to be placed in multiple positions all over the building to get a full set of measurements for our plans. This allows the laser scanner to gather very fine detail throughout the survey, creating an almost photorealistic and millimeter accurate 3D data set. We can navigate through this point cloud by picking scan positions throughout the property to help us find specific details that need to be communicated, as well as confirm we have all the data we need to put together our final product. RTC 360 is a super fast scanner capable of gathering 2 million measurements per second, up to 330 feet away. Now we can touch on mobile scanners. And here are the scanners that I am most familiar with, the GeoSlam ZEV Revo and the Leica BLK Go. First, this is the GeoSlam ZEV Revo. The trade-off for a less colorful point cloud or a hyper level of precision is that with a mobile scanner, you greatly reduce your time on site taking measurements, because scanning is done continuously while walking through a space and does not need to be mounted to a tripod. Even stacked up against the Leica scanner we just discussed, 3 hours of scanning can be cut down to 15 minutes with a mobile scanner like this one. These scanners are also very modular, and you can mount other equipment to them like a GoPro camera, or even mount the scanner itself to a drone. This is the newer model from Leica, the BLK Go. Between this and the scanner we looked at previously, there are some pros and some cons. For example, this produces a much more photorealistic point cloud, but the level of precision is less finite. In the next slide, we'll see a short video of a scan taken with the ZEV Revo. You can easily see that even though there is no photo-based colorization of the points in this little villa here, these points are colored on a height lamp, where points at different heights are shown as different colors on a spectrum, which you can see on the left. Red is lower height, blue is higher. Coloring the points this way makes it easier to see important features in the point cloud, even without the photo colorization. So let's talk now a little bit about mobile scanning and processing. Using a mobile scanner is preferable if your time on site is limited. Once the scan is complete, you need to use the SLAM algorithm software, which interprets all the measurements and movement data from the scanner and produces the 3D point cloud. Since most individual scans take only 15 to 45 minutes, this will give you time to process the scan on site to check your results before you leave. Reviewing your complete point cloud on site is essential to ensure accuracy. Most errors in scanning or processing can be spotted pretty quickly, and actions can be taken to ensure the overall accuracy of your project when the time comes to draft or model. So now let's talk about this infamous point cloud. Reviewing your data well before attempting to create a set of as-built from a point cloud is a must. If there are any kinds of errors with your cloud, which do happen, then using that bad data can either stop you in your tracks later when you're drafting or modeling, or even worse, result in an incorrect set of as-builts. Once your scan is processed, you'll need to review the output. Did you cover all the areas? Can happen that areas are closed off or not known, hidden walls, doors. Are there any flaws or errors in the scan, such as drifting? Got to ensure there's no drifting in the cloud. Make sure to look for any of this drifting, which can occur when the software has trouble putting all the points together. If this occurs, then you can try some reprocessing options or simply scan the structure again. Drifting is common with mobile scanners, and it occurs for several different reasons. Determining which reason is helpful before attempting to reprocess or rescan your project. You can see in the lower right-hand corner of this image, in a great example of drift from the exterior due to lack of access all the way around the building. We're going to go through a few other examples of what drifting or other errors might occur. In this case, the bathtub on the left is incorrectly showing itself to be in the kitchen area. The vanity on the right side isn't in line with where it should have been. See where the arrows are, and the arrow on the right is clear due to the empty dark space. There may have been an internal error with the scanner in this case, and in fact, I know it was because this was an issue that happened with our scanner a couple of years ago and since been resolved. But heavy drifting in the neon textured area shows that something is wrong and can confuse you later when drafting or modeling. You can actually see here where it twisted all the points and created a kaleidoscope almost with the data. There are tons of drifting errors in this one. Placing walls exactly would be difficult. You can see there are duplicate lines shown. It makes it near impossible to discern what is real versus what is scanner error. Some problems, though, aren't as easy to spot while in the field or slowly reviewing a point cloud. Problems, unfortunately, can become apparent when you are performing your drafting or modeling work, and you discover the data the scanner collected has those errors. If the mirrors or a really reflective surface aren't covered, then it will mirror that part of the scan behind it. So in this picture, it is a bathroom on the left side and a hallway on the right, where the vanity in the bathroom and the bathroom door are mirrored into the empty hallway, showing data that is not really there. When scanning attics, foundations, large sites, or multi-level structures, you may run into issues getting all your data to fit together. Areas that are hard to access or have lots of reflective surfaces, as we just recently discussed, or have fewer unique features like office hallways or open and empty spaces can all pose a challenge. Processing requires all areas have data that's connecting one area to the other, so they can be properly glued or stitched together. Mirrors, moving objects, etc., can also trick the process and therefore give you bad output. The screenshot you see here is of a multi-level structure and is a space with fewer unique features. And additionally is an open and empty space. And it did actually pose a challenge while on site. Most scanners have a range of hundreds of feet, which can produce a lot of data outside of your project area that you don't need. You may need to clip or crop your point cloud to reduce the file size by getting rid of that unwanted data. If you have to produce multiple point clouds for a large or complex project, it will be important to get comfortable with point cloud software that will allow you to merge or register your clouds and more easily manage your data. Much like traditional methods of sketching and measuring, properly scanning a structure does take a lot of practice in some cases to do correctly and efficiently. Once you are practiced with scanning and know what to look for when those errors have occurred, you will have the most reliable versions of data you can gather in the field. You can be confident that the as-built plans you create will be fully accurate and ensure a smooth and safe renovation as it progresses. Now we have the point cloud, we've collected it, so let's talk about using it. Now that you've processed and reviewed the outcome of your point cloud data, we'll need to do one of the following two things. Do it all again if it came out poorly, or Bring your point cloud to your drafting and modeling station to get started with the next phase. Sections. In order to produce items such as a floor plan, you need to be able to slice the point cloud into the desired section and work from that. Most software allows you to do that quite easily. And then you need to be able to view it from all directions. In addition to cutting the sections, you'll need to be able to move and rotate the clouds to give you the working angle you desire. We're going to get into creating the as-built set in our next session, but here I have some slides that can display just how you can get acclimated with the point cloud with the photos you've taken on site. Here you can see a 360 photo on the left, which allows you to pan around in a full 360 degrees around you. If it was safe enough to get up on the roof with the scanner, you're in luck, and you'll have some excellent data to work with in drafting or modeling. It's always good to have photos open while you do this, regardless, to ensure it's correct. Scan data from inside an attic can also be very useful in displaying the behavior of the roof, either if you need to do work up there or if the roof is not accessible. Looking in section throughout the project or even before you start your work is a good idea. You'll be seeing the structure in a way that you can't ever see in person. Having point cloud data is extremely beneficial over measuring with traditional methods when sections need to be created for the plan set as well. In summary of the second section, scanning your project can reduce errors and time spent on site. The type of scanner you use will be dictated by your needs and level of detail required. Your scanner will create a cloud made up of millions of points. Knowing how to manipulate it is crucial. This way, it will have utility once brought into your preferred software. As an added note, my perspective has been that almost overnight, as-built production methods have shifted from traditional, or done that way for decades, to utilizing the latest in laser technology. As with every new introduction of production methods, there is a learning curve, but once mastered, the entire process gets much smoother. And when incorporated with BIM technologies, the entire construction process can get a boost in speed and efficiency. Drafting from the point cloud. When drafting from the point cloud, the first thing you'll need to do is get into the drawing environment. This can be imported directly into AutoCAD or Revit, as well as other architectural software. Note, if you use Autodesk products, you'll need to use an application called Recap to prepare the point cloud to ensure it works within their entire software suite. Drafting from a point cloud in CAD is pretty straightforward, but it does take some getting used to. There are lots of options in CAD to color, slice, crop, move, and rotate the cloud in different ways. And you'll need to use the view queue to regularly adjust your UCS orientation properly to work with the cloud in different positions. Point clouds are ideal as-built data sets for creating Revit models, but the Revit point cloud tools can feel a bit lacking. If you're making a 3D model, it only makes sense to work from a 3D point cloud to create an accurate model to kick off your designs and planning. The tools for visualizing the point clouds are not as robust as they are in AutoCAD, which is a little weird, but nevertheless, point clouds and Revit do go hand in hand. First, we can talk about drafting the plan view items from a cloud. When drafting in CAD from a point cloud, you'll want to ensure that your cloud is positioned orthogonally so that you can use the ortho function in CAD to draw lines. Positioning your cloud on the Z-axis in CAD is also desirable for several reasons. You should be able to derive all the walls, doors, and door swings right from the point cloud. Window information can be found as well when you are skilled at reviewing clouds. Many scanners will not pick up smaller items though, especially if they are flush with the walls or ceilings. Trying to locate them in the cloud can be very time consuming in that case, so oftentimes it's better to revert to the traditional method while in the field and just sketch and measure these items. All right, now let's get into drafting other views such as an elevation from the cloud. This is where there is a huge advantage in having a complete point cloud for drafting. Provided that you were able to access the roof in scanning, you will have a complete picture of not only the roof behavior, but also every height you'll need to properly draft your roof. Excuse me, 1 second. My apologies. Also, every height you'll need to properly draft your roof, exterior elevations, and any section you might need. As with electrical and RCP components, our reflected ceiling plans, sometimes it's beneficial to revert to traditional methods to sketch ornamental items you'd like to include in your drafting. Now let's talk a little bit about the Revit. The level of development system was created for the AEC community to put standards on BIM drawings. It rates the precision, the detail, and overall refinement you can take your model to. With level 100, the lowest, meaning you just mass your objects roughly, and level 500, the highest, being so detailed and exact you are essentially building a virtual version of the structure. When modeling as-built plans, LOD 2 to 300 seems to be the applicable range, since you are assessing a structure that has been built from the outside. All interstitial spaces are inaccessible, and their construction cannot be assumed. Similar to drafting in AutoCAD, the first thing you'll need to do to work with a point cloud in Revit is make sure it is in a recap project format for use with Autodesk products. Using the point cloud to guide modeling in 3D can be more complex than drafting in 2D. However, the benefits of having all elements of the building related to each other in 3D can be valuable to your design and planning process. Viewing the point cloud and model in 3D provides a lot more information about how structure, MEP systems, and architecture interact. Modeling an as-built in Revit may seem overwhelming at first, but a solid order of operations for creating a usable Revit model will go a long way. First, let's talk about modeling the plan view items from the cloud in Revit. When modeling in Revit from a point cloud, you want to ensure that your cloud is positioned orthogonally in plan view so that you can use the appropriate tools to make sure to place the walls orthogonally. Then set the finished floor to your 0, 0 level, and then create and set all other levels to key features in the point cloud, other levels, the plenum, top of roof, etc. Once you're done setting the finished floor, you can start adjusting your view range and view depths in your plan views to add wall, door, and window families in the places indicated by the point cloud. Vertical information. As with AutoCAD, this is where there is a huge advantage in having a complete point cloud for modeling. Drawing sections and adjusting section depth is crucial to viewing point clouds effectively when adjusting window heights, door heights, and creating roofs. Practice patience. Roofs are tough to model, but even more so when you want them to accurately match a point cloud. There are some advantages to having a BIM as-built, which some may not know. Sometimes a three-dimensional model is only considered for a presentation for design purposes, but it can also be useful as an as-built as well. The as-built BIM model can be viewed in multiple phases, so you can easily switch between existing, demo, proposed, and alternate proposed phases. When you have a BIM model, moving from the design phase to the construction documents phase of a project is far more efficient. Having an as-built BIM model can make it easier to understand a project that you haven't visited yourself, since you can cut sections, view into your interior spaces, and review roof massing, all in 3D. Some say Revit offers a more intuitive design experience and allows users to present 3D images at the planning stages to the owner or planning departments. So to sum up the final portion of this presentation and the presentation altogether, drafting from a point cloud into CAD is a pretty straightforward process. It takes time to become efficient, but you'll just be working with the point cloud into 2D CAD, utilizing the CAD tools to move the point cloud into 2D views. Drafting from a point cloud in both CAD and Revit means that you'll be importing the cloud itself directly into the software and essentially tracing or placing components right on top of the cloud to create your set of plans. Modeling in Revit can be difficult if you're not practiced, but once experienced, it can save time and be very useful throughout all phases of the project. All right, so quick Q&A. Go ahead and put your questions in the chat, or your answers in the chat, and we have a couple other polls. But my question to you is, when you went to school for architecture, did you have any sort of classes that you could take on as-built, how to properly measure a building or anything like that? I know I didn't, but trial by fire. Yes, you did? Awesome. Where did you go to school? No, no, no. Lots of no's. Nope, no classes. Yep. It's all on the job training, right? Oh, historic American building survey courses were often. Awesome. That's really cool. Sub question. How did I do on explaining the process for those that did have some classes on it, or based on life experience before the earthquake? That's funny, Walter. Somebody did ask a question in the chat directly to me, but I'm going to answer it live. It says, how do you scan pipes and wiring behind walls? Essentially, we can't. We do not have X-ray technology. Basically, if we can see it, or it, we can scan it and document it. But if it's behind a wall, that we don't do. Our electrical plans just show outlets, switches, things like that. Our reflected ceiling plan shows the fixtures themselves. We don't show any wiring or piping that connects, the toilets, toilet plumbing, or HVAC ductwork, again, unless it's visible. We have had some commercial projects that we've scanned with RTC that document piping for some industrial projects. Pricing. There are some pricing on our website. I don't want to get too much into that, as there are a lot of complexities that can create a range. We do have some single family and commercial pricing on our website. Happy to follow up directly with individuals on specific costs for projects that you might have. Approximate cost of a mobile handheld scanning equipment, anywhere from 35,000 to, well, 30,000 up to 70,000. As far as I'm aware, there are some that are more expensive than that, but that's why we exist, because we do lots of them every day. So we can pay that return on investment off pretty fast. Low cost options for small firms. Essentially, there's lots of options. I talk with a lot of my clients, some of which are on this presentation and in the chat. But talk to us, tell us what you need. There is an economy of scale that, and a minimum cost for us to go out. But we can make things work for doing just a floor and maybe portions of buildings. We try to do at least a floor for different scopes. But good question. Happy to talk more offline about low cost options, places to take classes or learn LiDAR scanning. Honestly, not sure. We do all our training in-house for our surveyors. I do know that some of the manufacturers of the different kinds of equipment do some direct to user training. I'm not sure of any others directly that just do LiDAR scanning training. Were there any other questions in the chat? Happy to take more questions. We've got quite a bit of time. I actually finished up a lot faster than I was anticipating. Since I don't see any other questions yet, I'm going to actually move on. Just curious, how long would it take your team to measure and draft a 1,500 square foot single family residence? What should we be prepared to pay for as built of a 5,000 square foot interior space? Again, I would probably direct you to the price ranges on our website. I can follow up directly with you, Alan, to give you specifics, but each scope is a little different, and we require a minimum of floor plans to do others. So you can kind of use the baseline for that, but floor plans only for AutoCAD, we charge somewhere in the neighborhood of 30 cents to 70 cents a square foot for floor plans of a single family residence. Commercial jobs range from 8 cents up to 50 cents a square foot for floor plans. But again, any other additional scope on top of that would be additional 10 to 12 hours modeled in Revit. So that, Justin, is that 10 to 12 hours, the measuring and the modeling in Revit? And how much detail do you go into in that Revit model? Roughly 200? $16 hours. 300 to 350 is your goal? Okay. Yeah, 10 to 12 hours is pretty darn close to what our time probably would be for the same, but again, depending on how much scope. What is time comparison, field sketching and develop CAD drawings versus field scanning and develop 3D model? Good question. I think it kind of goes to, thank you, Alan. Looking forward to it. Time comparison. It's been a long time since we've done it by hand. It also depends on how much detail you're capturing in that site visit. What I will say is that for a 1,500 square foot house, for us to entirely do the site visit process, we'd probably be talking about 2 to 3 hours and maybe 6 hours of drafting and maybe a little bit more in modeling. Thank you, Valerie. Does that include potentially having to revisit the site once you get? Yeah. How often do all of you have to revisit a site to capture more information? Yes, I will actually skip ahead here. There's my contact information right there. I will also take that. Oops, sorry, went away. I will also copy and paste that in just a second here into the chat. Unless Joel and Amber, you're on, can you copy my contact information into the chat real quick? Yeah, also depends on unique conditions of the building. That's a big factor even for us, depending on the scope. Reflected ceiling plans, electrical plans, even the geometry or how much stuff is in a house can make a little difference. Not as much for us laser scanning as it is by hand, but certainly it's a factor.